share my desktop here. And we'll walk through the kind of a walkthrough on the Parasite drag tool, and some of the features, key modeling, and then we'll go through a real quick simple demo, a couple of simple demos, kind of a walkthrough on a simple airplane, and then go through the validation case, which is the S3 Viking. Yes. There we go. Is that better? Okay. Objectives for the development of the Parasite drag tool, really to, for anybody who's done a Parasite drag buildup, a traditional workbook method, you use to big, long spreadsheets, big, complex spreadsheets to capture everything that you want. And so a lot of a bookkeeping exercise. I took a snapshot of the drag workbook that's up on the VSP Open VSP wiki page, and that was a really good initial connection between an Excel workbook and the Open VSP geometry. But when we started to look at developing the Parasite drag tool, we wanted to go a step further. How can we make this even faster, more accessible? Reduce the time it takes, improve geometry fidelity based on traditional just workbook only methods, provide a validation case to help build some artifacts and build confidence in the tool, allowing people to have it be their go-to tool, and then to make this scriptable, so that you can start exploring the design envelope, different trades on initial trade studies. So those were our initial objectives going forward with the development of the Parasite drag tool. Our approach was to basically bring a lot of the workbook method into the Open VSP GUI, and really provide kind of a very familiar interface. So you see this a data table layout that a lot of people are used to seeing in a Parasite drag buildup, and a lot of the common parameters are right there in front of you. So uses existing geometry equations. It uses existing VSP geometry, friction coefficient equations, form factor equations, flow conditions to get that overall buildup. Try to do provide a good amount, a good variety of those equations to allow the users to select their favorite, or the one that's most applicable for their particular design case. And then we've got the ability to export to a CSV file. So if you do want to bring it into another tool, be it an Excel workbook, be it another analysis tool or a MATLAB script that wants to read in a CSV file, and provide some documentation cases. And I'll go over where that documentation and where the validation cases are available. A little overview of the GUI. Over here on the left, we have the overview tab. This is where you're going to select, what geometry set you want, the typical shown or any of the sets in the set editor. The model length unit. A lot of the equations are based on. This is really one of the tools that really starts requiring a unit here for length, and so if you've modeled in feet, you can select feet. If there's inches, meters, a variety of units here available. The equation selection for friction coefficient for the laminar and turbulence is next, and then reference area right after that, and you can set reference area from model as needed, or you can set it to manual here. And then the flow condition, there's also a variety of different flow conditions that you can specify. The US standard atmosphere is shown here as the default condition, and you can change various parameters here, and even change this around to reflect maybe the condition on Mars, or maybe the condition in a particular wind tunnel, if you're trying to match some wind tunnel results. And then at the very bottom is the main execution buttons here, to allow you to calculate the parasite drag, and then the main other action is to export down to a CSV file. The buildup table here on the right gives you just a summary of all of the geoms that you have in the selected geometry set, and then their buildup onto the right. You can sort it by component, you can sort it by wetted area, and you can also sort it by percent total. You can select some different groups here, different grouping treatment. The form factor equations are settable here, and then you can set percent laminar flow and the interference factor, and then there's also some additional settings depending on the group and form factor equations. The excrescence tab is right here next to the overview tab. You can see as you switch from overview to excrescence to documentation, the buildup table always remains kind of front and center. So you can see what your changes are doing to the table, and how the excrescences are getting added in. So it's always front and center. The excrescence list gives you various options for adding additional drag that's not represented by particular aspects of the geometry. Drag counts, drag area, percent margin. Those options are all shown here, and I'll walk through adding some of those in a demo of those. And then next to the excrescence tab is the documentation tab, and this gives you kind of a quick reference for what are the parameters. So you don't necessarily have to go to an external site. You can go look up what some of these symbols are, what they mean, right here within the software. And then down here, there is a link to the wiki, which further documents the parasite drag, the equations used, and references. As far as the equations that are used, for the laminar, there's only the Blasius equation, and then turbulent, you have several other equations here. A lot of the in-depth information here is provided on the Parasite Drag wiki. I won't go into any of these in detail, but I'll let you. It is available on the wiki site. And then here's just a comparison plot of those different friction coefficient equations plotted against Reynolds number, and a lot of them line up fairly on top of each other. I think in the first iteration of early iterations of the Parasite Drag tool, there was an error in some of the equations. That's since been fixed, and here's the latest version of the friction coefficients. Form factor equations used. There's also a plethora of different form factor equations. Again, a lot of their references and detailed information are on the wiki. Several different ones for the wing, as well as for body type components. And their plot is shown down here in comparison plots.
Hey, Nick, I'll jump in. There were some bugs with the implementation of these when these plots were made, if you both for the form factor and the CF equation. So if those haven't been updated, they look a lot better now.
And then one other common item that I did want to point out here is the geometry alignment. The tool doesn't make any to be very quick and easily accessible. The tool doesn't make any distinction between a pod. It assumes that pods and wings are aligned with the flow direction. So I just put two different pods into a particular model and ran them through the Parasite drag tool, and you can see here they come up with the exact same drag contribution. There's no deriving or inferring the pod orientation angle. And so when you do put a pod in, or you do put a wing in, or if you're using a fuselage component to represent a landing gear strut or a stack component, those things are going to, when you have those complex geometries, the Parasite drag tool is going to assume that it's aligned with the flow. A fuselage would be aligned longitudinally with the flow. So be careful there and make sure you have the expected results that you're wanting to see. For instance, if you are trying to do that landing gear strut, like a typical kind of a bent aluminum landing gear strut that's on a Cessna or something, modeling that with a wing component would work fairly well to align with the flow. I just take you through an order of operations here, going from adding the geometries in the basic OpenVSP geometry browser, getting your model set up, and then coming into the Parasite drag tool. You get here by going to the analysis menu, going down to Parasite drag, and this window will pop up. You'll select your geometry set, what units you're in, your equation preference, and kind of fall through this list to edit your options as needed. Then you'll then go through and over to the excrescence tab, add your excrescences as you have them defined, and then go ahead and set your flow conditions. And if you want to change your various atmosphere parameters, and then the final step here is to come in and calculate your CDO, and that'll allow you to just get the quickest way to get into your initial buildup. And then you can go in and when you hit calculate CDO, if you have a really complex model, it does run CompGeom behind the scenes when you click on it. So it may take a few seconds to go through, depending on how tessellated your model is. And then the table will populate, the buildup table will populate to the right. So just give it a minute. If CompGeom works, this tool should work just fine. And then you can use the scroll bar. Scroll bars will pop up kind of as needed, and to see the rest of your options. If you come up with the final results and you see, oh, where are the rest of my items, it's likely that your window just got size just isn't capturing it all. So you can scroll to the right. I've also found on some monitors just slightly resizing the window will allow everything to pop up. Microsoft Windows seems to refresh and get the right size, figure out the right size of the window. The changes to the free stream properties can be adjusted. Changes to interference factor, things, those can all be adjusted. Addition of excrescence can all be adjusted after calculating the CDO. But if you do change geometry, like changing the wingspan or changing a pod length, that you'll need to rerun calc CDO, and so it can rerun CompGeom and get new wetted areas. So that'll be one thing. Some stuff you can change on the fly without having to rerun CompGeom. But sometimes you will need. Safe result is to just kind of quick calculate CDO, just make sure you've captured everything that you do want. So I want to take you guys through just a simple demo before I get into the validation case here in a second. Bring up my new version, new instance of VSP. And so for this demo, we'll just add everybody's favorite airplane, a pod and a wing. And we'll add at least one more wing and move it to the back. And here we'll want to add, we can add a control surface. And you'll see that subsurface pop up in a minute here. So going to the analysis tab and pulling up Parasite drag, you see that the GUI populates, and you can see that some of this isn't sized, doesn't come up. Kind of quick trick here is to just resize your window, and sometimes that allows it to pop up. I also did notice changing one of these boxes allows it to resize again. So once you got your kind of window all set up, you can expand these. And as I expand this aft wing geom, you'll see the subsurface did come up. And that allows you to give it some separate treatment for that particular area, or set it to a zero drag area. So we're going to do all shown geometry. Let's say we're in feet. We'll do from our first wing geometry, and we'll just go down to 250 feet per second. Calculate CDO, and you can see that this takes a minute, but it did go through and populate. And then you can adjust interference factors, and those populate in real time. So you don't necessarily need to rerun calculate CDO. And then you can sort by wetted area, you can sort by percent total, and back to component. And there are, it will come up with the available form factor equations here as an option, and you can go through and pick your favorite form factor equation, and that you'll see that the answers populated without having to run calc CDO again. Going to one of the validation cases that we looked at developing this was a Lockheed S3A Viking. There's a technical report that provided a nice build-up, component-based build-up, traditional drag, with some based on some wind tunnel test results. Quite a few hours of wind tunnel testing. This was done back in the early 1970s. The reports down here, I was able to get aircraft dimensions from this reference, and they did find a reference to the specific airfoils being used at the root and the tip. And so that's what I based the VSP model on here. And then I did two, you can see the nacelles here are bright green. I modeled those in two different ways, and I'll go through those in a second. But this model I did upload up to the VSP hangar if you guys want to follow along. The VSP modeling, I approximated it from just a basic 3 view. It took a little time tweaking the model for the workshop this year. I updated the airfoils. Adjusted the layout to better match some of the images, and then I added the aft nacelle as well as the wing pylon. Those were also referenced in the the wing pylon was also referenced in the paper. So I want to make sure that the model was complete. And then the cowl or the nacelle was modeled both as a body of revolution and then as a duct. And you'll see the differences or between those two. The nacelles were also modeled with a zero drag interior flow. So I set a subsurface here on the leading edge, a rectangular subsurface that goes basically from the leading edge to the trailing edge for the whole inside of the nacelle. I did that for both the bypass nacelle and the aft nacelle, aft duct. And you can see those here down in the Parasite drag. And then for the body of revolution, I built up through the Parasite drag tool, built this up and then exported the results to a CSV. I only cleaned it up a little bit by adding some borders here, so it dropped into the presentation nicely. But this is basically what you get out of the Parasite drag tool in terms of just opening up the export in Excel. And then I also added here on the right the reference CD, the components from the report, as well as the difference between the report and the Parasite drag buildup. In total, this was about 10% off, 10 to 11% off. The excrescences here I included directly from the report, so those match with zero error. But the geometry, just based on the geometry with the body of revolution, we're getting about 11% error. The one thing that I didn't do, because the paper didn't reference in terms of the percent laminar flow of any of the components or any of the interference factors, I left all of these at the default factor. Now I know that's optimistic in terms of the drag buildup. So for what it's worth, those are all documented here, and you can kind of play around with how well using your best engineering practice. I'll leave it up to others to see how that impacts. And then the duct model, you can see here had to change the form factor equation type, and then but overall this matches about 1% better than the body of revolution model, just between the two cases. And you can see going up and down. Overall, getting this within about 10% without adjusting for any of the interference factors. Certainly we are under predicting here on the fuselage component by about 20%. That can easily be taken up by having to add in the 20% interference factor here. So far, for kind of a quick and dirty tool, this turned out fairly well. And then I did from the 2019 VSP workshop, this item right down here, the wing store pylon, that one's a new one. I did put that in, and the geometry is up here as well. So you can play around with that and look at that. And then, as I said, the model is available on the VSP hanger, and I set the source quality good for a drag buildup, and based on just publicly available 3-view drawing. I'll just show you guys. I know I've got about 4 minutes left. I'll show you my VSP model here. So this is the S3 model here, and I have the body of revolution no show right now. But those are essentially the same, pretty close to the same surface. I have them pretty highly tessellated as well. So it takes a second to run the Parasite drag tool. But I have a couple of sets set up in here so that I can switch back and forth, and then the flight condition in here as well. You'll see as I click Calc CDO, this takes a second to run, because it is running CompGeom in the background, and calculating all the new wetted areas. As soon as that's done, it'll populate all the wetted areas, and then you can see this is in this example, I have the subsurfaces here that are treated as zero drag, and you can feel free to click those and see how you can set it the same as the parent. Separate treatment. Is it quits? It's still pending. Or to zero drag. And then it gives you the kind of the real-time buildup down here at the end. And then the export down into the CSV file, just opening this up. This is what it gets you right out of the CSV file. And then you can pretty this up again, and you end up with these tables. So it gives you a very quick way to go through and get your first Parasite drag buildup, and get some initial results, get an initial CD knot, so you can move on to other tools like VSPAERO. And all of this is integrated with the API and scripting, so you can call it. You can call these analysis functions from the API. You can set up each one of the equations through the different enumerators through the API, so you can automate this as you're automating different designs. And there is a set of unit tests that go and plot the data for the atmosphere, the form factors, and the friction coefficients. And then again, the documentation is available here on the OpenVSP wiki. Any questions?
Thanks a lot, Nick. Someone did bring up a question as to what the difference between how VSPAERO is calculating Parasite drag with its kind of basic setup to add that in, and the capabilities of this. Now, obviously, this is quite a bit more detailed and gives you more design freedom, but do you recall off the top of your head what the formulation for Parasite drag is in VSPAERO, or will we just leave that for Dave tomorrow?
Let me answer that one.
Okay.
So VSPAERO only calculates Parasite drag in vortex lattice mode. It doesn't do anything in panel code mode. In vortex lattice mode, it actually does something similar to this for both bodies and wings. For bodies, it has a simple skin friction Reynolds number equation. For turbulent, it calculates the Reynolds number on the body. It calculates the local velocity of the component as a whole, and it calculates, and it has a form factor that it calculates for the bodies. For wings, it actually treats the wing, and also for rotating propellers and rotors, it treats the wing as in a stripwise manner, calculating the local velocity, the local Reynolds number, and applying a simple, it amounts to a form factor, but it's essentially data based on an NACA 0012 out of theory of wing sections. For a full airplane, I think it's reasonable to say you could just ignore the Parasite drag out of VSPAERO and use the Parasite drag buildup instead. This will give the main advantage that any other excrescences that you are including, like if you're adding in antennas and landing gear and flap gaps and roughness and things like that that are not actually modeled by the physics, you'll have a way to capture them. However, the one really, really great thing about the one built into VSPAERO is when you're doing something like rotating blades on a propeller or a rotor, it's able to calculate that local velocity coefficient, that local velocity and local Mach number and local drag as the velocity varies out the radius of a blade, and calculate that drag so that it actually increments the power required of the rotor, based on that Parasite term, not just the induced term. And so, and that's of course something that you wouldn't even be able to get out of a normal airplane analysis for that Parasite term. So Kenny and I have talked about it, and we think that in the future we'll want to go towards sort of a hybrid mode, because of course that VSPAERO model doesn't know anything about all of your excrescences, and since it's just a vortex lattice, it doesn't know anything about anything you leave out, like any booms or landing gear or other components that you leave out of the model. So we eventually need to go towards a way where we use part of the Parasite drag analysis and feed that as a basic drag term into VSPAERO so that it gets rolled in. But right now they're separate things.
Thanks a lot, Rob. That was a really good distinction to make, that rotating bodies and things, it does add that stuff in. So I appreciate that.